Sairam. Welcome to the next session. Let us quickly review what we had seen in the last session. We had looked at two specific operations. One was called as vector addition, and we also looked at scalar multiplication. Remember that we used these two operations in order to define what is called as a linear combination. This same idea of linear combination that we discussed in the last session, we performed only on two vectors. It can be extended to any finite number of vectors. So when we say a linear combination of vectors v1 to vn, then we're talking about c1 v1, c2 v2, and so on up to cn vn, where c1, c2 up to cn are real constants. They are real constants, and v1, v2 up to vn are those column vectors which we had defined earlier. We say column vectors, remember they are just written as a single column, numbers written from top to down. And one more point to remember would be that we have scalar multiplication involved here in c1 v1 or c2 v2 etc., and we are having vector addition where we written as the symbol we have written as plus is vector addition. Okay, let's now look at how we can represent them geometrically. But before we do that, one simple point to remember. Let's talk about scalar multiplication. We say 2 times the vector 1 2, then we know that the answer is going to be 2 4, another vector. The important point to note here is that the scalar multiplication between this constant and this vector is defined by real number multiplication by the components of the vector, as simple as that. So we take the constant 2, multiply each of those components, and that is obviously defined because that is simple real number multiplication. Okay, now let's proceed to the geometric representation. Okay, so let's take the vector 2 1, and let me try to represent this vector on the real line. So we are looking at a 2-dimensional vector. Remember, we have not defined the term called dimension, but very informally we understand what is meaning of dimension. We are saying the number of components that a vector has is probably the dimension. We will look at the official definition of it much later. Okay, now that we say the vector is 2 1, how I represent the vector is, so 2 units on the x-axis and 1 unit on the y-axis. So let me start at the origin and draw a line till that point and put an arrowhead there. So this is my point 2 1, and remember each vector we represent by drawing a line starting always at the origin, and we draw a line till this point and put an arrow there representing the direction of this vector. Now also remember that we have two things associated with the vector. One is its magnitude, or this length, how much we travel from the origin to this point, as well as the direction. So anytime you move from a place, we are talking about how much to move and which direction to move. So with this in mind, we will look at what happens to scalar multiplication in geometry. So let's apply a scalar multiplication. Let us just double this vector. So the answer we're going to get is 4 2. Now let's try to represent 4 2 in the real plane. So in 4 units on the x-axis. So if you want, you can also do this way. You can move from the origin 4 units on the x-axis right here, and from here we can move 2 units on the y-axis. So I moved horizontally 4 units, and then I moved vertically 2 units, and therefore in order to represent this vector, which is 4 2, let me draw a line from the origin to the ending point, which is 4, 2, and let me put an arrow there. Now we notice something very interesting. We see that the vector 4, 2 and the vector 2, 1 are pointing in the same direction. In fact, the vector 4, 2, the vector 2, 1 is overlaid on the vector 4, 2. Let's pick up one more example. Let's say I have the vector 1, minus 2, 1, minus 2. Let me try to represent this. So 1 unit on the x-axis and minus 2 units on the y-axis. Therefore, I'll move down in the y-axis here. So this is my point 1, minus 2, and let me draw a line from the origin to this point and draw an arrow head at that point. So this is my vector 1, minus 2. Let's say we double this vector. Now we know that the answer is defined by real number multiplication to each of the components. Therefore, the answer is going to be 2 and minus 4. Let's try and represent 2 minus 4 on the real plane. So 2 units I moved from the origin on the x-axis, and since it's minus 4, I had to move down now. Therefore, I moved down to 2 minus 4. And therefore, what would happen now is if I start from the origin and try to draw a line right till here, pardon me for that very straight line, but what we can understand is that 2 minus 4 and 1 minus 2 are pointing in the same direction, and therefore what should be our conclusion? I mean, we can go ahead with further examples. You pick up 1 minus 2 and let's triple it, and therefore we will be getting 3 and minus 6, and you would find that it would still continue to some point here, and it may be a minus 6 here, and this would simply continue, which means that our conclusion is scalar multiplication does not change direction of the vector, does not change the direction of the vector, or the resultant vector happens to be in the same direction as the original one. Okay, let us proceed to vector addition, and let's see what happens geometrically for vector addition. So let me pick up 2 example vectors, 1, 2 and minus 2, 1. Let's see what happens when we add them. First, let's represent 1, 2. So here we have in the x dimension 1, and this is the 2 units in the y-axis, and therefore let me try and draw this properly. Okay, so this is my 1, 2 vector, 1, 2 as 1, 2 vector. Let's now draw minus 2, 1. Minus 2 is here, minus 2 on the x-axis, and minus 2, 1. So here. So this is my 1, minus 2 and 1. So this is my second vector. So that's my second vector, which is minus 2, 1. Sorry, I had to slightly shift my diagram down. So we still are working with the same 2 vectors, 1, 2 and minus 2, 1. How do we add them geometrically? So whichever way we want, we can take this and perform. Let's say that first we have started at the origin and you have walked to, you're starting to walk on the real plane. So you have walked to the point 1, 2. How did we walk? We walked 1 unit on the x direction, followed by 2 units up on the y direction, and we reached the point 1, 2. When you want to add another vector to 1, 2, let's begin here and walk in the direction of the next vector. So which means we will have to walk parallelly to minus 2, 1, which means that from this point, what happens if we walk parallelly with respect to minus 2, 1. So if I walk parallelly to minus 2, 1, I would reach this point, and this happens to be minus 1 comma 3. So if you use a graph sheet and try to plot it, you will clearly get the answer saying that it is a minus 1 comma 3. Okay, there's one more way to do it. Instead of first going from the origin to 1 2, let's first go to minus 2 comma 1. That means that I walk 2 units in the negative direction of x and 1 unit in the positive direction of y, and I reach this point minus 2 1. Let us now try and travel from this point in the direction which is parallel to 1 2, If I move in the direction parallel to 1 2, again I am going to reach the same point, which is minus 1 comma 3. And if you want to represent the vector minus 1 comma 3, we draw a line from the origin to this point minus 1 comma 3. So this would be my resultant vector, and you can see the parallelogram law of vector addition being applied here, and we can easily understand this geometrically. So here is my representation of the resultant vector minus 1 comma 3, and in geometry we are able to understand this quite clearly. And what we call this is the parallelogram law of vector addition. What we'll do next is we'll pick up the same two vectors and see what happens with subtraction. So we have the same two vectors 1 2 and 2 minus 2 1. Let's now look at subtraction. We'll try and look at subtraction. Let's first understand how the concept of subtraction is represented in geometry. So we are saying that from the origin, first I have moved to the vector 1 2 or to the point 1 2, and we would like to subtract the vector minus 2 1. Okay, let's not worry about subtraction now. Let's understand the concept slightly differently. Let's say that this is my vector A and here is my vector B. Minus 2 1 is my B vector, 1 2 is my A vector. We understand vector addition. Let's say that I have started from the origin and I have moved on the B vector and reached this point called minus 2 1. Let's ask ourselves, how much do I need to move from this point so that I can reach this point 1 2. How much should I move here, and in what direction should I move? So what vector should this be is the question, right? Okay, so we have moved from the origin on B, reached the point minus 2 1, and we are asking the question, how much do I move from B in order to reach this new point or the A vector position? So this is what we are looking at right now. The answer is going to be A minus B vector. The answer is going to be A minus B vector. Why would that be? As simple as this. Remember that this is nothing but vector addition. What is vector addition? When you want to add two vectors, we first walk on one vector and from there we walk parallelly or in the same direction as the second vector. Now let's see what we do. We first walk on B vector, so B, followed by we have walked on A minus B. So what is the summation? B plus A minus B is going to give us the resulting vector, which is A. And that's it. This is how we define subtraction. So see how cleverly we have defined the A and B so that we get the answer here as A minus B. So how do I get my actual numbers of the answer? All I need to do is to pick up this A minus B vector and draw it from the origin in parallel. So let me attempt drawing this in parallel to that direction and for the same distance, and see what do we get. So we are at the x position of 3 and seemingly there is a y position of 1, and if we do it mathematically, you will find that our answer is right. Now let's pick up the same example, but I have reversed the vectors. Please note here I have reversed the vectors. This time it's going to be a minus 2 1 minus 1 2. We still have marked them as the same vectors. Here I have the A vector and the B vector. Again, let's understand the concept of subtraction being defined as vector addition. So again, let us start at the origin and let's say that we move in the vector direction of A. From there, if a question is asked, how much and in which direction should I move so that my resultant answer, my final answer is the B vector. And the answer is by using vector addition. First we move on A, and from here we slowly, let me try drawing it straight, we move to this point, and this is our answer. What and how much did I move from the point 1 2 in order to reach minus 2 1? Let's forget the numbers. Let's look at vectors A and the final result being B. So first I have moved A. Obviously I should have moved B minus A, and that is when my answer can become B. Therefore this must be the B minus A vector. And if I draw that resultant vector parallelly from the origin, then I would reach this point here, which happens to be minus 3 and minus 1. Now you could ask me, how are you so sure that you will reach only this point minus 3 and minus 1? So here is a simple answer for that. Look at this resultant vector, which is B minus A vector. See where it starts. I am only looking at the x coordinate of this starting point, which starts at 1 and goes in this direction, goes till minus 2, which means in effect if I move the starting x point to 0, it must have moved by 3 units in the negative x direction. That is what we see here. Similarly, let us look at starting points y coordinate and the ending points y coordinate. We see that this is a 2 here, and effectively it has reached 1, which means if I move to the origin, effectively I should move by 1 unit in the negative y direction, and therefore we will reach only minus 3 minus 1, and there is no doubt in that. Okay, let me ask you a question. Let's say that I have the C vector here. You can see that there is a C vector here, 3 1, and I have another D vector here, which is a 2 minus 2. Now if I ask what would be this vector E, please do not give me a numerical answer. Please tell me what is E defined using the D and C vectors. So how do I figure that out? First I have walked on C, and I have walked additionally something so that my result is D, which means I should have walked D minus C, because C plus D minus C is my resultant vector, which is D vector. Similarly, you can ask the same question and see what happens if I start from the origin, walked in the direction of D, later somehow I have to reach C, so what should be this? Then you will figure out very easily that the answer this time is going to be C minus D vector. So let me ask you another question. Vector addition or say vector subtraction, do you think it will change the direction of the resulting vector, or it could change the direction of the resulting vector, or it doesn't change the direction of the resulting vector? So the answer is going to be that it could change, or it can change the direction of the resulting vector. Now why is it that we are not saying that it will change or it doesn't change? We are not saying these two. So can you try and figure out examples where adding two vectors does not change its direction, does not change the direction of the resultant vector? And can you find out an example where it will definitely change the direction of the resulting vector? Obviously, we have seen examples in this regard. Maybe you could look at how does this case arise. So let us summarize what we have learned in this session. We find that scalar multiplication does not change the direction of the vector, whereas vector addition can change the direction of the resultant vector.